Recording started.
All right, welcome back, Chem30 students. We're going to basically start back up where we left off with the last video. And so here we were on question number 9. And let's have a look at this question here. It says, match a name, excuse me, or a term from the list above, with each descriptor given below. So let's look at the different things we're looking at here. We're looking for the name of reactant 1. We want to find the name of reactant 2. We want to find the type of reaction that's taking place and the classification of product 2. So we want to find all those things, and we're kind of using the same principles we were going through just recently. Now to figure out what the products are, we're going to have to figure out what these reactants are, right? Once we figure out what these reactants are, we'll be able to know what type of reaction is taking place. So let's go on to the next page and figure that out. Well, here's the first of the reactants that we're looking at. So which kind of compound is this? Well, the basic structure comes from methane, right? Because methane is 1 carbon. And so its name is going to be related to methane. And it's actually a type of carboxylic acid because remember those have a double bond to O and a single bond to OH. And so we know because it's a carboxylic acid, remember the name of a carboxylic acid is going to end in oic. Okay? So because of that, its name changes from methane to methanoic acid. Okay, so this is methanoic acid. And now we're going to look at the second compound and find out what its name is going to be. Now, its name is also going to be related to methane because it also has 1 carbon. And now because it has an OH group, that's an alcohol group, so instead of methane, it's going to be methanol. Right, so that's what that is, methanol. So basically we have a reaction taking place between methanoic acid, which is a carboxylic acid, and an alcohol. So what kind of reactions take place between carboxylic acids and alcohols? Well, this is going to be an esterification reaction. So esterification reactions always take place, again, between carboxylic acids and alcohols. Here's an example of one. We have acetic acid, so that's a carboxylic acid. We have this isopentyl alcohol, which is an alcohol. And we've got our product, which is going to be the ester produced. So notice that the ester bond forms at the place where the OH group is joined to carboxylic acid. So here's the carboxylic acid, here's its OH group. This place right here is going to join to the other place that has the OH group. Okay, so that's going to be the bonding point between these two acids, or these two compounds, I should say. So remember, it's the place where both have the OH group. Those two OHs are going to be removed to produce the water. So again, this is an esterification reaction that produces a ester compound. With that kind of as a background, let's get back to our original question. So here was our original question. Okay, and so this is the question here, and again, it's an esterification reaction. And the compound, again, is going to be the ester produced. Now, let's think about how we're going to name the compound that's produced. So again, we know that this here is methanoic acid. This is methanol. How do we name the ester group that's produced? Remember that the root of the name comes from the carboxylic acid, the methanoic acid. Okay? So instead of calling it methanoic acid, we change it to methanoate. Okay, that's the first thing we do when we name the ester compound. We take the carboxylic acid name and instead of being methanoic acid, we change it to methanoate. The prefix that's going to go in the beginning, again, suffix goes at the end, prefix goes in the beginning, that's going to be based on the alcohol, whatever it's named. So because it's a methyl group, it's going to be methyl methanoate. Okay, so from the alcohol, we have this methyl group that's part of it. So that is where the name comes from. So it's going to be methyl methanoate. And again, this methanoate comes from the carboxylic acid. This methyl comes from the alcohol. So be sure that you know how to name ester compounds. Let's look at a similar question then to the one we just did. This question asks us, what will the reactants in the products be, and what type of reaction are we looking at here? So again, we know this is a carboxylic acid, this is an alcohol, this is the ester. Now in this situation, we have ethanoic acid, because the root of it is going to be ethane. Excuse me. Because ethane has 2 carbons in it, so it's going to be ethanoic acid. This is going to be ethanol, because again, this is related to ethane as well. Okay, so what's the name of the ester going to be? We will go on the next page and find out. Okay, so again, remember the root of the name comes from ethanoic acid, so it's going to be ethanoate. The prefix, again, is related to the alcohol, which has an ethyl group on it. Okay, again, we see the ethyl group. This is basically an ethyl group attached to the alcohol. So the name then is going to be ethyl ethanoate. Okay, awesome. Now we're going to look at a few different questions that are not quite the same as the last two. This one says, when aqueous bromine is added to hexane and to hex-1-ene, in the presence of light, a reaction occurs. So first of all, it asks us what type of reaction does hexane experience and what type of reaction does hex-1-ene experience. Before I do that, I just want to quickly go over something. I didn't answer this part of the last question. It says, what type of reaction is this? Of course, this is an esterification reaction. I just wanted to mention that as well. Okay, so back to this question. We're talking about these 2 compounds and what type of reaction do each experience. So we'll focus first of all on hexane. Okay, now, so we know it's single bonded. We know it's not an addition reaction because we know addition reactions require double or triple bonds in order for them. Those bonds need to be broken, and then we can add something to them. We know it's not an elimination reaction as well, because remember, elimination reactions are breaking compounds down into 2 compounds, more simple ones, and that's not what's taking place in this reaction here. Okay, so again, this was just a review of what addition and elimination reactions look like. You should be able to know these kind of basic equations for each one of the different reactions. So what I would do when you're doing a test, be able to write that down so you know the basics of what each reaction looks like. Okay, so it's not those 2. Well, we know it's not a esterification reaction. It doesn't involve carboxylic acid and an ester, but it is a substitution reaction. Why is that? Okay, remember, a substitution reaction is when there's atoms of 2 different compounds and they're being swapped. And that's what's going to take place here. So what's happening is the bromine is going to take the place of one of the H's. Okay, so when we're talking about hexane, these are going to be H's, and this bromine here, both the A and the Z are going to be B's from bromine. They're going to take the place of the H's, and they're going to go on here. Okay, so the bromines are going to go here. So So we already saw that the substitution reaction was for hexane. And now what type of reaction is hex-1-ene going to experience? Well, we know that it's got a double bond, and we know that addition reactions involve adding to double bonds. So again, those double bonds are broken, and we get alkanes as the products. So again, if we write down all four of these different types of reactions, we'll know that the fact that we have an hex-ene, hex-1-ene, we'll know that we have a double bond that we're starting with, so we recognize that we're going to have an addition reaction. Okay, question number 13. It says cycloheptane and cycloheptene are colorless liquids. One method used to differentiate between the two is to add a few drops of orange-colored bromine to samples of each organic compound. So we need to fill in the blanks here. Okay, so it says when bromine's added to these compounds, the cycloheptane undergoes one type of reaction, and the cycloheptene undergoes another type of reaction. All right. Well, we know from the last question that the ane, so cycloheptane, is going to experience a substitution. Okay, so remember we saw that before. Just kind of a reminder. We saw a substitution with the hexane. Okay, so it's the same thing, whether it's hexane or in this situation it's cycloheptane. Again, they're both anes. They're going to both react in the same way, and we're going to have a substitution reaction. Whereas a cycloheptene is going to experience an addition reaction because it's an alkene. Okay? Again, remember, whenever we have double or triple bonds, we can have addition reactions. Next question. We've got an ethene gas reacting with chlorine gas. So the first part is tell whether it's an addition or substitution reaction. The second part is predict what the product of the reaction will be. So, is it an addition or substitution reaction? Well, again, we saw that because we have ethene, it's going to be a double bond. We know then we have addition reactions. Okay? So then we're going to go and look at part number 2. So part number 2 says predict what the product of the reaction is going to be. Okay, so we're told that we have ethene, and so we draw it out, and it looks like this. And we're going to break the double bonds, and we're going to add chlorine to each of the carbon atoms. And so what's that going to look like when we do that? It's going to look like this. So here we see that we have single bonds, and we have chlorine bonded to each of the atoms. Okay, so again, we started with ethane, or rather with ethene, and now because we have single bonds, we have ethane, but because it has two chlorines bonded to it, we have dichloroethane. And so one of the chlorines is on carbon 1, the other is on carbon 2, so the name is 1,2 dichloroethane. Okay, awesome. So on to question number 15. This one here says two properties that cyclopentanol and pentanoic acid have in common. Okay, so the first part says they have the same number of what? Is it oxygen atoms or carbon atoms in their parent chain? And then the second part is going to be answered by this. So what we need to do first of all is to draw these compounds, and then we can answer the questions. So cyclopentanol, what's that going to look like? Well, the basic root of it is a pent, which is a 5-carbon compound. But we also know it's going to be a cyclic compound. Okay, and we know that because it ends in OL, it's got an alcohol group on it. So a 5-carbon ring compound with an alcohol on it. Now it's really important to be able to know how to draw these and to draw the number of carbons that you're going to have and the number of hydrogens. We can see that because this carbon is bonded to this, it has one carbon-to-carbon bond here, another here, it's going to be able to have 2 more bonds to hydrogens. So 4 bonds in all because they're single bonds. Okay, so be able to draw cyclopentanol. And then the next compound, which is pentanoic acid. Well, because it ends in oic, it's a carboxylic acid, which tells us that it's got a double bond to O and a single bond to OH. Now the root of it is pent from like pentane, and so pentane would have 5 carbons, as we can see here, and then we've got the carboxylic acid on the end. We have to assume that it's at the end because the name doesn't suggest anywhere else. Okay. So these are our 2 compounds, and now we can answer the question. So the first thing we were looking at, do they have the same number of oxygen atoms or the same number of carbon atoms? Well, they both have 5 carbon atoms in them. Okay, so the answer is going to be either C or D. They don't have the same number of oxygens. This one has 1, this has 2. Now both are going to be aliphatic. Okay, we know that aromatics are benzenes, and everything else, whether it's straight chain or cyclical rings, are aliphatic. Okay, so both are aliphatic. We don't have any aromatics involved here because there's no benzene rings. Okay, so question number 16. It's talking about benzoic acid, and it says to state the functional group it has and whether it's aromatic or aliphatic. Well, we know that because it ends in oic, we know it's a carboxylic acid that's involved, like this. Okay, so that's the functional group, a carboxyl group. That's answering part A. And where it says, is it aromatic or aliphatic? We know the benzoic acid tells us that it has benzene in it. And because it has benzene ring structure in it, it's going to be aromatic. And this is what benzoic acid looks like. Okay, sorry, I don't think I had anything else there. Okay, question 17. During an organic reaction, an unsaturated reactant becomes saturated. What type of reaction is this? When you look at this question, you might say to yourself, how do I predict that? Okay, well, let's take that a bit at a time. We know that the reactant we start with is unsaturated. That means it has double or triple bonds. And we know that the product is going to be saturated. Well, we know that whenever we start with double or triple bonds, that's pretty well always an addition reaction. Those double bonds are broken, and you end up with an alkane. So we have an addition reaction. That's answering the question here. We have an addition reaction. And we'll go on to the next page. And this is just a review of the elimination and substitution. It might help you to review them at this point. I'm not going to go into these in detail, but if you want to look on the whiteboard, or rather on the PDF file on page 47, you can review those again to help you answer the next question. Again, what I would do when I'm watching these recordings, I would watch them first of all and then try all the questions. So all these blue questions here, I'd try them again on the PDF file to make sure you can do them. And again, the questions on the test are going to be really, really similar. Okay, so next one. When a pentene and hydrogen gas undergoes an addition reaction, what type of product do we get? So we know that this is the basics of what an addition reaction looks like. And so basically what we're going to have happen, we have pentene, and it looks like this here. Okay, so it's 5 carbons. That's where the pent comes from. It's got the ene double bond. We know that afterwards, because hydrogen gas is being added, okay, so each one of these is going to be an H. H's are going to go on these 2 carbons. So all the carbons are going to have H's on them. And so we end up with this here, which is going to be pentane. So the product is going to be pentane. When it says what type of product do you get, you're going to get an alkane. And again, we know that because the H's are going to go on the C's, and this looks like an alkane, right? Okay, question 19, it says explain why 2-methylpropane and 2-chloro-2-methylpropane are similar in terms of these two different ways. Okay, so we'll start with A. We'll look at the branches found on them. And so, of course, what we need to do is we're going to have to draw out these compounds from their formula to be able to see how they're similar. So, we know that the basic root of this is propane, which has 3 carbons. Now, one of them has a methyl group, one of the carbons, and it's going to be carbon number 2 because it's 2-methylpropane. So again, a methyl group is CH3, so this is what 2-methylpropane looks like. And we're also going to draw the second compound. Now this compound, the root of it is propane, so again, 3 carbons. Now it's 2-chloro-2-methyl. So on carbon 2, we have a chloro group and we have a methyl group. That's why it's 2-chloro-2-methylpropane. Awesome. So now let's look at what the two compounds have in common. Well, here are the two compounds, and we're asking what the branches have in common. Well, this compound has a methyl group, and this compound has a methyl and a chloro. So both of them have a methyl group. So that's what they have in common. And the other part of the question says, what's common about the number of carbon atoms in their parent chain? We can see that both of them have a 3-carbon parent chain. Okay, question numéro 20, if you speak the français. Mine is not that good. Okay, question number 20. Compare cyclohexane, or hexene, sorry, and benzene as far as the number of double bonds and whether they are saturated or unsaturated. So first of all, we need to be able to draw cyclohexene. Again, the name hex tells us there's 6 carbons, and because there's one ene in it, and one double bond, it's right there. Okay, so be able to draw cyclohexene from the name. Also memorize what benzene looks like. Again, we know it's a 6-carbon compound. You know there's one H on each carbon. So the question says, compare them in terms of the number of double bonds. We can see there's 1 double bond here, 3 here. Okay, so we've done A. And next part, it asks us to compare whether they are saturated or unsaturated. We can see that this has a double bond and this has 3. Anytime you have double or triple bonds, they're unsaturated, so they're both unsaturated. Okay, question number 21. It says, which of the following rows identifies the structural diagram and the corresponding UPAC name with the chemical formula C8H16? So what we're going to have to do is we're going to have to take the fact that we're looking at C8H16. We're going to have to be able to draw each one of these and find out how many carbons they have and how many hydrogens they have. Because you can't tell that looking at the way that the molecules are drawn right now. So let's draw the molecules properly then. The first one then is ethylbenzene. Well, we have to memorize what benzene looks like. Again, it's got H on each carbon. Because it's got an ethyl group, and we know an ethyl group has 2 carbons on it, this is the ethyl group, so that's why it's ethylbenzene. Now we can count up our C's and H's. We know there's 6 here, there's 2 here, so that's 8 carbons. We count up the hydrogens, and we find that there's 10 of them. So the formula is C8H10. That's not what we're looking for. We're looking for C8H16, so it's not answer A. Let's look at the next one. So for B, excuse me, ethyl cyclohexane. So again, it's a cyclohexane. There's 6 carbons. They're in a cyclic structure. There's an ethyl group coming off, which has 2 carbons. So it looks like this. Again, be able to draw it. Again, we count the carbons and the hydrogens now. We count 8 carbons. When we count up the hydrogens, we get 16. So at this point, we could stop because we found the magic formula C8H16, which is what we were looking for. And again, remember, we needed to draw all the H atoms in order to solve this problem. Okay, what we're going to look at now is are what we call general formulas. Okay, so for instance, alkanes, straight chain alkanes like this here, what's the general formula you can use to predict the number of carbons and hydrogens? It is CnH2n plus 2. Okay, so in other words, the number of hydrogens are twice as much as the number of carbons plus 2 more. So here we have 3 carbons, so it's twice as much, which is 6, plus 2 more, which is 8. Okay, again, it's twice as much because each has 2 hydrogens, but there's 1 on each end, so that's where the extra 2 comes from. So here's the general formula for an alkane, and now we'll go on to alkenes. So alkenes, we have 2 less carbons. So instead of having 2n plus 2, the formula just has 2n. So those are alkenes. With alkynes, there are again 2 less. So it's 2n minus 2. All right. And those are all the straight chain general formulas. How about a cyclic alkane? Here's a cyclic alkane. And if you count up the carbons, you can see there's 5. Hydrogens are 10. So again, it's CnH2n, double the number of hydrogens. So you can see the general formula for a cyclic alkane is the same as the general formula for a straight chain alkene. It's kind of cool. Okay, we can also predict that for the cyclic alkene, instead of being CnH2n, it's going to be 2n minus 2, and for the alkyne, it's going to be 2n minus 4. Okay, so let's just summarize them here. I'm not going to read them out, but you can see them summarized. And I apologize, I didn't make these as kind of subscripts. I just kind of ran out of time to do that, but you can think of these as being down below. Okay, so question number 22, we're getting close to the end, guys. It says a student added a bromine solution to a hydrocarbon sample that contained an isomer C6H12. After shaking the sample, they observed the color of the bromine solution change from orange to colorless. Okay, so basically we're adding bromine to excuse me, to C6H12, and we're going to get some product. So we want to answer each one of the questions about the hydrocarbon C6H12. Is it saturated or unsaturated? Am I coughing or am I going to die? Anyways, okay, so part B says, is it hex-2-ene or cyclopentane? So we're going to answer part B first, because answering that is going to help us answer part A. So because we're told that it's C6H12, there are 6 carbons. So because there are 6 carbons, it's got to be the hex formula and not the pent formula, because hex stands for 6, pent stands for 5. Now if it was a pent sort of formula and it had an extra methyl group, that would work. But there's no implication of that here. So the formula is going to be hex-2-ene, answering part B. And when we look at whether it's saturated or unsaturated, because it's an ene, it's a double bond, and so it's going to be unsaturated. That answers part A. Okay, great. So moving on to question 23. Which of the following rows identifies the condensed structural diagram or line diagram and the UPAC name of the isomer C6H12? So again, we're going to have to take formulas like this, or rather structures, diagrams like this, and we're going to have to be able to add the carbons and the hydrogens in order to be able to find out whether this diagram is one that fits with C6H12 or not. So let's notice, first of all, with C6H12, the formula, magic formula we're trying to find, it could either be a hex compound, which has 6 carbons, okay, like this one or this one, or it could be one of the pent compounds because they both have methyl groups, so that's an extra carbon. So that's 5 plus 1, which is 6. So moving along, we're going to start with D actually, and we're going to go up to A. So you'll see why in a sec. So here's D. So D here, you can see that there's 1, 2, 3, 4, 5, 6 carbons, so C6. If you add up the hydrogens, you will see that there's 10, and we've not found the magic formula C6H12, so it's not D. Likewise for C. You can see that there's 6 carbons, 10 H's, so again, same formula, but it's not C6H12, so C doesn't work either. Now for B, we're going to have to draw this out. We know it's a hexene, so we know that it has 6 carbons because it's a hex group. So we know it's a cyclic compound, and because it's got 1 E and 1 double bond, it looks like this. So now we can draw all our carbons, all our hydrogens, and add them up. So 6 carbons, got the C6. If we add up the H's, we got H10, still not our magic C6H12. Guess it sounds like it must be A. Hopefully it is. Anyways, so here's methyl cyclopentane. And again, when we draw all the appropriate hydrogens that come off here, remember it's got a methyl group, so we have to include that. Okay? So then when we add up all the carbons, we get C6H12. So that's the right formula. And so again, remember it's really important to draw all the carbons and hydrogens to answer this sort of question. And it looks like we're done. Awesome. Okay, so thanks guys for watching this whole thing all the way through. And again, practice all these questions over and over again. Make sure you can get all the questions that are on this recording here, and then you should be able to do the questions that are on the test. Again, practice the questions on the PDF file. If you have any questions based on any of this, please let me know. Other than that, keep up the hard work. God bless, and have an awesome day. Bye for now.